So here's this like pinkish violet one. Here's this blue one. Here's this green one. I don't know what this one is yet. And here's a red one. Oh, these are so cool. Yeah, so these two are really dim, aren't they? I mean, not super dim, but they're just not glowing as much. They're not emitting light as efficiently as these two are. Okay, so let's look at this one. I don't know if this is another purple one. Yeah, this is another one. That's that purplish, I believe. Here, let's take a look. Yeah, it looks similar, huh? Okay. So in all of these cases, what they have done, the people who create these, is they find different molecules where, when they are mixed together, the electrons get excited up into an excited state as soon as they're mixed together. But immediately they drop back down to lower energy states. Okay? And depending on the molecule, there might be a larger drop in energy that those electrons take. And if it's a larger drop in energy, that means it's more energy, and that corresponds to a shorter wavelength of light. And so that would correspond to the violet and the blue colors. So violet has the shortest wavelength of light that our human eyes can see in the visible spectrum. Blue is the second shortest wavelength of light that our eyes can see, followed by green. Okay, now after green is yellow, and then orange, and then red. Now what I was hoping is that I have in these glow sticks that there is yellow. Ooh, is there? This looks yellow. We're gonna check. I think this one. I think there's yellow. Okay, we're gonna try this. Okay, because right now this looks yellow to me, right? Now it might change because right now this is a dye and it hasn't been mixed with anything yet. Okay, but as soon as I break it, it could change slightly. Okay, so let's hear. Let's listen. Okay, so we've broken it. We're starting the reactions. And now let's shake it up. Lo and behold, I think we've got ourselves a yellow. How exciting. Wow. Look at that thing. This is amazing. I bought these glow sticks at Spirit Halloween store a year ago, and I never used them. Hardly at all. I honestly, I didn't even realize there were so many different colors in it. So thank you for experiencing this with me. And so exactly what we're seeing is that we have larger energy transitions for purple followed by blue, and this is going in the order of the rainbow. The only one we're missing here is orange, and it might have just been they didn't bother making one, or it wasn't that different from the red, or who knows what. But in any case, this red one has the lowest energy electronic transition, with those electrons that are excited dropping down and then emitting those red photons. For the yellow, dropping down at that exact perfect energy difference, the electrons drop down, corresponds to the energy of yellow light. So, eventually, these chemical reactions will be complete. They will reach equilibrium, and there will no longer be any driving force to excite any of the electrons. And so, as we know with glow sticks, that these will fade over time. But if they put them in some kind of gel, which is very viscous, and it does not allow the molecules to mix too quickly, then that can slow down the chemical reaction. And so that allows your glow sticks to last for longer than if this was in, say, water. So, some glow sticks, they last just 20 minutes. Some of them might go for an hour. So it just kind of depends on how they are made and what is in them. So when I take Neil to the dog park, I've noticed, and I don't know why I never noticed this before, but I think because now it's getting dark so early, but a lot of people have these glow stick collars, and they put them around their dog, and then they can see as it gets darker, they can tell which dog is theirs based on the color or the design that's on it. But yeah, that's a really cool idea, and so I was thinking I should do that. So things like those glow in the dark stars that you put up on the ceiling, those are a little bit different than this, right? Because these were excited by virtue of a chemical reaction. It was the chemical potential energy that then excited those electrons, got them excited and made them, and then as they do, they drop back down to the lower energy ground state, emitting a photon. And so with the stars you put on your ceiling, those, you excite the electrons by shining light on them. Those are those permanent, either usually plastic or the little stickers. And yeah, there's no chemical reactions with those, right? But you do have to charge them up, so to speak, shining light on them. And so what's happening with those, this is what's called fluorescence. So the electrons get excited, and very soon thereafter, meaning within somewhere between a second and a few minutes, the electrons then drop back down. And it also can be like on the microsecond scale or something like that. But fluorescence tends to happen much quicker than phosphorescence. So phosphorescence, on the other hand, like those glow stars, you hit them with light. So you turn on the lights in the room, or it's daytime and the sun is shining in the room, and the electrons in those stars, they get excited. Now in phosphorescence, the electrons get excited and they stay in the excited states for much longer. They can stay up there for many minutes. They can stay up there for hours. Okay, so it's called a metastable state, where those electrons can hang out there in that state and then slowly, one by one, drop down and slowly emit light. And so that's why those glow-in-the-dark stars that you have on your ceiling, they're sometimes still maybe a little faint, but they're still glowing after you've turned off the lights after several hours. Those electrons are still slowly falling from the excited state down to the ground state. So phosphorescence is a pretty amazing thing. It's a lot more rare than fluorescence. Fluorescence happens with many, many different molecules. But phosphorescence, you have to have a little bit different and more specialized kind of structure that will allow for phosphorescence to occur. It's still very, very awesome. I love anything that glows. I think that's why in graduate school I wanted to do something with colors. So I got into inorganic chemistry because transition metal complexes are very colorful. And I also wanted to do laser spectroscopy and photochemistry because then I would have to work in a dark room with glowing things. And I just loved the idea of that. So it's kind of like the room I'm in right now, right? I've got a dark room and I have glowing things, including my mic here. Nice glowing things. I've got my glow sticks. It's just, I'm kind of in heaven right now. So we can just bask in the glory of these fluorescent glow sticks and think about energy, right? Our concepts of conservation of energy that we talked about earlier, and energy absorption, energy emission, all that kind of stuff. Very relevant here. I had just mentioned laser spectroscopy that I did in graduate school, and that's another example of a specialized kind of photon emission that's called stimulated emission, where there is a photon. Is very interesting because a photon is hitting an electron that's already excited. And you would think that that electron would just get more excited. But instead, that photon is then promoted down to a lower energy state. And then two photons are emitted from that. And those two photons have very special properties. They have the exact same energy. They're traveling in the exact same direction. And because they have the same energy, they have the same wavelength. And not only do they have the same wavelength, but they are coherent. So where each wave has a peak, so does the other photon. Where each wave of a photon has a valley, so does the other one. And so what you get is this amplification of the intensity of the photons goes up when they are coherent in that way. And so that's why lasers are so intense, is that there's this amplification of the intensity of that light. And lasers always have one energy, one color, right? You see a red laser, you don't see white lasers, because lasers only have ever one wavelength of light that is emitted from them. So that's all tied in with these ideas of absorption and emission of light.